Today we start chapter 2, which is predicate calculus, and our section for today is 2.1, Introduction to Predicate Calculus. If you look at our lecture notes, you will see that this is far the longest section in our lecture notes. Usually our notes are like 3 pages long or 4, and this one is like 8-9 pages. And the reason why I made it so extensive is because it is really crucial that you understand the main idea of this chapter. So here is where we introduce that precise language that's much more elaborate than the language that we used in chapter 1, and that helps us actually to analyze mathematical structures. So, for example, let's say the following. In the predicate calculus, we had in the propositional calculus, we had something, propositional formulas like P implies Q. And we learned how to analyze the truth value of this formula or the appropriate statements according to the truth value of P and Q. So basically, P and Q were either true or false, and we didn't try to make a decision about it being true or false because there was no way to make that decision. We just said, if someone provides the truth value for P and Q, then we can decide if this P implies Q is true or false. We also talked about the structure of this expression. We used trees as well, so here's propositional letters P and Q. Here is P implies Q. And this is the symbol implies. So that was the summary of our story before. What will happen here actually, we will try to analyze P and Q itself. So we'll actually enrich them so that P and Q are not something that we expect from someone else, but actually they will now get a structure, and that structure will be some propositional mathematical formulas. So for example, let's say, what are those? Simplest one, just for the beginning. Let's say here we say 7 less than or equal 5, and then implies 7 less than or equal 9. So these are now mathematical statements, and they were formulated in a structure that we hopefully know or we investigate. And then if we can decide on our own if these statements are true or false, then we can carry out the same decision procedure as before. So for example, this is now propositional. This is now a formula for predicate calculus. So how would it look? It would look like this: 7 less than or equal 5 implies 7 less than or equal 9. So most often that's how our formulas will look like. So they will have enriched structure comparing to propositional formulas. So how would we decide now? We are not waiting for someone to tell us what the valuation is. We actually decide on our own. 7 less than or equal 5, we know that that's false. 7 less than or equal 9 is true. So false implies true is true, and that's our valuation of this formula. But then we can write now different formulas. So I'll formalize this a little more. Now I'm just going through examples. So these are called elementary formulas. So elementary formulas are built in a domain. So you specify a domain, and then you use some elementary formulas. You use our connectives from the propositional calculus, and there is one more ingredient, and these are quantifiers, and those are universal and existential quantifier. So that's basically how the formulas in this section will look like. But let's do one thing at a time. So so I just started the example. So we fix the domain. So what is our domain? we fix a structure that we are analyzing, and then we know something about the structure. What are the elements, and what are the operations, what are the relations between the elements. So let's say here, our domain, let it be z, integers. What do we know about z? So we kind of introduce symbols that we want to use to write formulas. For example, we know that there is some operation addition, there is operation multiplication, there are some constants, 0, 1, and so on. So if I want to express something about constant, we also know in that language, we know that there is some relation between integers less than or equal, so we know when is a certain number less or equal than the other, and that's it. So for example, if I say 5 plus 2 squared greater than 9 plus 1, like we did a minute ago, this is called elementary formula. Elementary formula. So there are no logic, propositional connectives or quantifiers or anything like that. There are just some constants, so these are constants. And then there is some relation involved, and then we need to make a decision according to our knowledge of that structure. By the way, I have a couple of troubles here. What are those? In the language that I introduced, imagine that language like you created symbols for the printer. So printer understands this symbol. My printer would be confused. What do I mean when I say 2 squared? And what do I mean greater than? Because I mentioned here less than or equal. So we also use less than, greater than or equal, greater. And what else? We use powers. So like operation square. Operation. So now my printer would understand what I said, and then the answer here would be false. Why? Because we know 5 plus 4 is 9, 9 is not greater than 10, so this is elementary formula. But what's even more interesting is the following elementary formula. Here's another elementary formula, x plus 7 greater than 10. So how did I build this elementary formula? I used constant, 7 and 10. I used a relation symbol greater than, but here I used the variable. X is the variable. So what happens here? Now I cannot immediately say true or false. I am actually waiting for your input to tell me how much is x. So generally sometimes program would say x equals, and they would ask you for the prompt. So, so what happens? Propositional formulas involving variables might change their truth value depending on the variation of that variable. So for example, if you put x to be 5, you will get 5 plus 7 greater than 10, which is true. But if you put x equals 1, 1 plus 7 is greater than 2, then that's false. So this is one of the main lines here to understand when we have variables, then the truth value often depends on that variable. And then here we can even describe all the variables that will make, this is a very simple example, so it's so easy to do it. We'll actually run this, how did I truth set? Okay, so truth set. Truth set is what? What are all these x's that will make this formula true? Actually, that's exactly what we do when we solve inequality, because x plus 7 is greater than 10. That's, we know that just happens if x is good. So truth set is set of all x's where x is greater than 3. By the way, what did I use here? I used set the builder notation that you are probably saw in your pre-calculus or other courses. So here is the set. I introduce the variable x, and then I have a line here, and then the description. Which x's will make this formula true? Those x's where x is greater than 3, or in the interval notation, if you remember, that would be 3 to infinity. It is. 3 is not included. That's why I put open parentheses. All right, so So we described the truth set, and now we will start analyzing formulas. Let me actually do another example. Phi of x. So now it's not gonna, so it's still the same domain. We'll look at the following formula, phi of x is x plus 7 greater than 10 implies x squared greater than 100. What happens here? So this is the formula that is built using two elementary formulas. Actually, we have a structure of this type. So this is an elementary formula, and this is another elementary formula. They both involve a variable x, so for different values of x they will be true or false. And then we have a formula that's obtained when we connected those two elementary formulas with the symbol implies. So one could say the following, that the structure of this formula is like this. There is implies here, and there are those two balloons that are just extended P and Q, and they are actually x plus 7 greater than 10 implies x squared greater than 100. So here it is. So now we'll do the same thing as before, so we'll keep feeding different x's, and then we'll see for which axis it will be true, for which axis it will be false. So when we feed particular x, let me feed x to be 0. What happens there? Then 0 plus 7 greater than 10, it will, that is what, false. And then 0 greater than 100 is also false. False implies false, will be true. But if you put, for example, x to be 5, then what happens? 5 plus 7 greater than 10, that's true. 5 squared greater than 100, that's false. So we get false. Here it is. So it works the same way as before. We specify value of x, decide on the truth status of elementary formulas inside the balloon, and then we finish the same way as before, that specifies evaluation, and then we use the table as before to decide this formula of the predicate calculus. This is almost as general as it could be in predicate calculus. The only thing, of course, sometimes it gets more complicated if you have more than one variable, a little longer structures, and then the last ingredient, of course, is still to come, and that is quantifiers, universal or existential. Truth set here, yes, we can describe here the truth set. Why? Because it's fairly easy again, because what happens is, x plus 7 greater than 10, that means that x is greater than 3. So we'll say the following, case 1. If x is less than or equal 3, then what? Then we have that x plus 7 greater than 10 is false. And then you remember from propositional calculus, anything from false, so on the bottom of the decision, at 3 we just use our propositional calculus, so the whole statement, so phi of x will be true. Case 2. What happened? We know x squared to be greater than 100 for positive numbers. That means that x is greater than 10. So now the second case, if its x is greater than 3, but less than or equal 10, then what will happen? X plus 7 greater than 10, that's basically what we did here. X plus 7 greater than 10 would be what? 2. X squared greater than 100 will be false, so the whole formula will be false. And finally, case 3, What if x is greater than 10? Then x squared is greater than 100. So anything implies true, because which is true. So anything implies true is true. So what we saw here, and there is a misprint in the notes, I just noticed this morning. So what is the truth set? Set of all x is such that what? X is, where's the case 1? X is less than or equal to 3. Or x is greater than 10. No, this was good, but in the notes, in the interval notation, I used the wrong parentheses, so it would be negative infinity to 3, it should be square brackets here, union from 10 to infinity. I think in the notes I put square brackets here, parentheses here, which was wrong. So that's basically how this part of our today's lecture look like. Then what? So what is the story when we start introducing quantifiers? So we use two quantifiers. I can erase this now. You got that idea. There are two quantifiers. One of them is like letter A upside down. It's called universal. It's mean for all. And then this one, like E left, right, is existential, which is exists. So it's very important to understand them, how differently they behave than just, let's still keep the same domain so that at least that part is not changing dramatically. So let's analyze the following statement. Let's analyze the following statement. That's example 213. Every x squared is greater than or equal to -5. Let's first analyze what is the syntactical structure of this formula, and then how do we make decision about the truth value. So generally, if I were to draw the structure of this, it would be the following. You have elementary formula, are all balloons, x squared greater than or equal to -5. And then there is universal quantifier for every. So here is what happens. How do you decide about this formula? This time, I'm not waiting for my user to tell me how much is x. I actually here at the end, I will just have immediately true or false. So what do I do here? I keep running all the elements from the domain. If it's 0, the integer, if it's R, it's all real numbers. So basically what I do I do the following. I take x equals 0, x equals 1, x equals 2, 3, and so on. And of course negative on the other side. And I have to test all of them. Is -3 squared? Yes, true. -2, true. -1, true. 0, true. And then what happens? If I always get true, of course you can ask me how would I test all of them. So sometimes we need conceptual analysis and not just, I cannot plug in all these numbers, but you know that. So sometimes we rely on something that we generally know. So whatever number I put here, whether positive or negative, I'll get true. So if I get true for all the elements on the domain, then I say, yes, this statement is true. If I get once, I get false, I'll just stop trying to justify that. I just say false. That's called counterexample of the universal statement. So for example, if I say the following, so this statement is true. Next example. If I say the following, for every x squared greater than or equal to 10, then what do? You start again, 0, 1, 2, 3, 4, and so on. So for example, let me just start from 4, pretending that we don't know what's going to happen. So if x equals 4, 4 squared is greater than 10, I got 2. And then I keep trying to justify it, but if I put 3, I get false. Here I stop, and I say that this statement is false. As I said, this element x equals 3 that showed me that my universal statement is not true is called counterexample. So to decide if universal statement is true or false, you have either to run in maybe some generic way all the elements from the domain and show the statement is true, or just find one counterexample showing that it's false, and that's it. You just say that the statement is false. It's very important that you notice that here I didn't ask how much is x. I was running either one procedure or the other. A minute ago, I was waiting for x to be supplied to me to give answers for, so answers are given for particular x. We said answer depends on x. This is just one answer at the end. So either universal formula is true or false. I run through all the elements, but generally at the end, I just give one possible answer. So that's why it's very important that you make a clear distinction between the previous case. So if I say like this, x, what do we have, x plus 3, oh, what was the previous one? X plus 7 greater than 10 implies x squared greater than 100, then I'll say, so if this was phi of x, for some x's true, if you remember, for some false. This is the case where we have x is a free variable. On the other hand, on this statement, for every x squared is, we say that x is bound variable. That means just I don't wait for anybody else. So it's not gonna depend, does not depend on x. Does not change with x. There is only one answer. True or false. There is a similar situation that you experienced before, and that is, for example, if you have like this, like integral of x squared dx is x cubed over 3 plus c. So I get a function, and that function value of the function depends on x. So that's like a free variable. So this x, an indefinite integral variable, is free. What about if I have definite integral 1 to 3 x squared dx? Then this one really does not depend on x. Why? Because when I finish calculation, x disappears, and that would be what? 9 minus 1/3. So that's like 26/3. So basically, it's very important because if I were to rename the variable here and start calling it z, then nothing's gonna change. Because just this is like a scaffolding variable. It just helps you to reach the result, but at the end it doesn't appear in the result. Here, if you change the variable, then if for example, when you do change a variable method, at the end you have to go back to the old variable. So that's a huge difference between those variables that involve quantifiers. So that's a universal quantifier. What happens with the existential quantifier? this. Existential quantifier works quite the opposite way. So, example, if you, it goes like this, there exists x such that x squared is greater or equal to 10, then what? Now again, you run through your structure, but then what happens? If you find one x where formula is true, you immediately stop. So here you only need one supporting evidence, and that supporting evidence is called witness. So for example, if I put x to be 5, 5 squared greater or equal to 10 is true, that's it. That 5 is my witness. So I'll say what? That the whole formula is true. Of course, there are sometimes more than one witness. And that's it. Or, if I run through the whole structure and show that there nobody will satisfy, then I would say that it's false. So for example, so this one is true. Here is an example where you deny existential quantifier. There exists x such that x squared is negative 7. Then what do? You just keep running through everybody, 0, negative 1, negative 2, negative 3, and you square each of them and you see you never got negative 7. Of course you can say, how can I write all of them? Or you use conceptual reasoning, so you always get false. So if you somehow show that there's no way to find a witness, then this formula is false. Again, it's a bound variable. That means only one answer. You don't say, for some x, and no, this one at the end has just one answer, true or false. So at the end, x is not something that you need to feed in. All right. And then, by the way, if you look in my notes, or in our notes, you will see that there I was writing, I think that's called, in Ebb's book they do it, for every x in z more often. I like more this shorter notation where that z is not specified here because it's just like a context. So I know that I'm working in z, so I don't have to specify it. So some people like to specify it all the time. Maybe here on the board I use the linear notation. We know that we are dealing with z, so there's no need to specify it all the time. All right. So that's general story how the formulas look like. And now what we want to learn is when we have a text, how to write the propositional formula. That's somewhat tricky. And then, or the other way around, when we have a propositional formula, how to estimate if the formula is true or not. So, so here's one example. Example 210. Difference of two irrational numbers is irrational number. So how would you write a predicate calculus formula that kind of represent this statement from just a mathematical statement, but expressed in everyday language? So here it is for a domain. This time we'll take all the real numbers. And then within real numbers we want something that we call predicate. So predicates. Predicate, that means some object have it, some not. And predicate, we can use either predicate being a rational number or being irrational number. So let's use more kind of nicer predicate. Predicate q of x, q, which means what? Q of x is true if x is a rational number. Okay. All right. If we have that, we have enough language to say what we wanted to say here. And this is a little tricky. So you see, quantifiers are not always explicitly mentioned in your statement. They say difference of two irrational numbers. So someone say for any two irrational numbers. That's what one would hear. You might disagree with this, but he says difference of two irrational numbers. So someone makes statements and say, oh, if you take two irrational numbers, their difference will be irrational. So basically, really there is universal quantifier here. So what? Obviously we are talking about two numbers and we need their names. If they are specified, I'll use those constants. If they are not specified, I use x and y. So x and y are two variables. They stand for two numbers. Not rational, irrational. I just say because property is not part of the name. Name just is x, y, z, and then whatever property the object has, you put later on. I notice very often that people want to build property in the name. Alright, so what happens? So now we are telling the story. Alright, so what do I know about this? So what do I know? Know about x and y. They are irrational. So that means that they are not rational, so not q of x. I also know not q of y, and I put conjunction. And that says, so I still have, I'm not talking about the difference, so I'm saying the following. I know about x that it's irrational, and I know that y is irrational. Then their difference will be irrational. So here is their difference. I have minus in the language. It's also irrational. So I take one irrational number and another. Their difference is also irrational. And then someone says, and that's always true. So for every x and every y, and now something very important. If I put it like this, you are not sure if those every x, every y are referring only to first one, to these two, to implication. So it's very important that you put parentheses. And if I want them to rely for to refer to everybody in the statement, here's how you should put parentheses. This is crucial. And you can see immediately why it's important. What if I put parentheses here? Because the way it looks, both my variables are under the influence of these universal quantifiers, so all the variables are bound. That means at the end my answer is true or false. If I were to put parentheses here, then those two appearances would be bound, but these two would be free, and obviously that would not be the same. Here is this is the statement expressing this fact. And basically what happens, how would you decide true or false? I will show you that it's false. I'm not saying that this is automatic. Oh, that's trivially obvious to see. Basically what? If I will just give counterexample. This statement is, by the way, false. And here's the counterexample. I will choose x to be 2 plus root 2, which is irrational. I will choose y to be just root 2, which is irrational. But when you take their difference, you 2, which is hash. So you see in my example, I have not q of 2 plus root 2, and I have not q of root 2. So this statement says, oh, their difference will also be not q. No, but I have q of their difference, 2 plus root 2 minus root 2. Since I found this counterexample, the statement is false. I know that this is not absolutely trivial, but this is what you need to learn, and it will take a while, so don't get frustrated that you cannot immediately start writing this afternoon, but it is just progress to be made. And then let me now do what we asked in that example, actually, to find, this statement looks a little, I wrote it a little differently than in the lecture notes, so just learn it whichever way you like, whichever one is more kind of appropriate. I think this is better than what I have in the notes. Anyway, they also ask us here in this example to write a negation of this statement. So write the negation of this statement. So what would that be? You can say, that's easy, just put negation in front and that's it. So now I will put the negation here. And now comes the following property. And that property is precisely formulated in the notes. Here I will just apply it. Negation can go inside the formula, and the rule says the following. When negation goes through universal quantifier, then it makes it existential quantifier. So generally, I will do it, and I'll try to explain a little bit why is that, and why is that in sync with what we know from before. So negation is traveling inside, so every x becomes exist x. Every y becomes exist y. And then I have the negation of the propositional part inside. I better keep it in outside part. Negation here, and then not q of x, and not q of y, implies not q of x minus y. What now? Oh, first let me explain why is that. That the negation of a universal quantifier actually gives us existential quantifier. You can use common sense or analogy. Because what does it mean that not for every x, a of x? So if you say it's not true that everybody has property a, that's the same as there is someone who has the opposite property. If not all the swans are white, that means there exists a swan that has a different color. Or the same way, if you go negation of exist ax, that means it's not true that there exists object with a property a, that means everybody has. So if there's no swan, if someone says it's not true that there exists one that's not white, that means all the swans are not white, which are white. All right. One can connect, this is actually generalization of the De Morgan's law. Why? If you think, what does it mean? Let me erase this. If you want to say negation of for every x, a x, so that means, let's say, an integer. It's not true that everybody has it, that a of 1 and a in integers, and a of 3 and da 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 da. Very often we think of universal quantifier as infinite conjunction. Then if you apply De Morgan's law, you get not a of 1 or not a of 2 or not a of 3 or, which is what? The or is usually associated with existential. There exists x such that not a of x. So generally that property, how we negate quantifiers is actually nothing else but generalization of De Morgan's law. Let me finish this now. Kind of simplification of the negation. Now this is just propositional part, so we used our old tricks. So negation of P implies Q, because that's the structure, is P and not Q. So this is all P implies Q, don't look inside yet. So it will be like this: there exists X, there exists Y, so that first one copy the way it is, so that's your P. Not Q of X, and not Q of Y, and not Q of X minus 1. And that means there exists X, there exists Y, so that's not Q of X, and not Q of Y, and Q of X minus Y. And that's exactly actually what we proved a minute ago, provided an example. We found witnesses for that, X and Y, such that X is irrational and Y is irrational, and their difference is rational. So this is now simplified negation of our statement. Now let me try just one more example. Again, on that side where we have, we need to progress the most. Let's say the following. Yeah, let's do example 2.111. Where we have the following. So B of P means student P is B. You see, A of P, student P will take a manic, and C of P, student P will get extra credit. And we ask you to comment about for every P, C of P implies A of P. B for every P, B of P implies exists P. No parentheses out here. Implies there exists P such that A of P per C, there exists P such that B of P and A of P. The most important thing here to note structurally is difference between A and B. Why? Because in A, when you look at the structure, you have propositional part inside and a quantifier outside. Here is the other way around. Each of them has its own quantifier. You see, quantifiers are done first, and then implied is between them. So the third one also has quantifier outside. So, what happens with A? A says something that will be true for every student in our class. I think the domain is, well, I didn't specify the domain. Yes, we'll get an extra credit. So let's say this is our class. Okay. So this statement is something that, statement says something about all of you. And it says, no matter which student you pick up from our class list. If he gets an extra credit, that means he took the amatic. Or we can say the following, what? For every student, the only way to get an extra credit is to take amatic. I use here the old combination that basically amatic is a necessary condition. So for every student, and then I say what we know from before, amatic is necessary to get an extra credit. Part B, and that's true because that's what we said in our syllabus. Part 2 says the following. If this is, every student is busy, and then, and which is true or false? Let's say everybody is really busy in this course, so every P of P, all of you are very busy, so let's say that that's true. And then there exists student that, I hope that that's true, but you see I'm not establishing connection between this. So generally here I pick a student and then I argue for that student. Here I look at all of you and say, are you all busy? True or false? Then this, will someone take amatic? True or false? So each of them is decided individually, not student by student, just at the whole class, and then I make true, let's say that this is true. And then C is again, quantifier is outside, so I'm asking here, going case by case, is there someone in this class who is busy but will take amatic anyway? And I hope to. But I cannot say before